Hi, I'm Nate Adams, and welcome back to the Electrify Everything course. We're into part 5 now, so we have finally gotten to where we're going to be talking about HVAC, which stands for heating, ventilation, and air conditioning. This is the hardest part by far of residential electrification, particularly in cold climates, because many contractors are nervous about it, which I'll tell you a story about very shortly. So this is the first module in this, and this is the only part that has multiple modules. So we're going to be talking about reducing risk and proper sizing for HVAC. So here's where we are. We're in part 5, and we're in the first part of part 5. Okay, this is where conquering fear basically trumps all. So if it doesn't happen to be your fear, it is most definitely your contractors, particularly in cold climates. So about half of U.S. residential natural gas use is in 8 cold climate states. Well, it's technically 6 and 2 are coldish. But we have to be able to deal with heat pumps and sell heat pumps in cold climates, or there's no way we're going to pull off residential electrification, because literally half the problem is there. And let me give you an example of this. So one of our clients, he called a contractor that wasn't on our list, wasn't somebody we usually work with, and we had spec'd out a 3-ton variable speed heat pump for his 2,700 square foot split level, which sounds like utter insanity if you don't know me and you don't know what we're doing in the house, and you don't have all the background. So the budget was $14,000 for that piece of equipment. And the bid that he got back from someone that I didn't tell him to call was $23,000. He about hit the roof. He called me ticked off, and then I quickly responded, did you call somebody I suggested? Well, no. Well, then why don't we do that? So he called the guy I usually work with, and it came back at $13,500. And everything was smooth, and we went from there. But what that first contractor was doing was pricing fear into that job, because he was afraid of a bunch of different things. It was unfamiliar. He didn't know me. There was no trust level. The fellow that I usually work with doesn't even ask for load calcs anymore. So what size you want? Okay. And he puts it in. So one nice thing about Kevin that I normally work with is that he is a country contractor. So he lives in a rural area, as do I. And in rural areas, you have 3 choices for heat. You have heat pump, oil, or propane. So he's already relatively familiar with heat pumps, and they don't terrify him, where you get into the city and it's all furnaces and air conditioners. That's all anybody knows, because that's all that's installed. So we need to, like I talked about earlier in the scaling electrification piece, this is a land war. And we have to convert HVAC contractors one by one by one. So I'll give you a path to do that at the end, or maybe you'll be lucky and there will be an HVAC 2.0 contractor near you, because they're not going to fight you on heat pumps. But fear, this is critical. And how do you allay fear? It's usually knowledge. Knowledge and understanding. So let's take a look at this. We need to be able to reduce risk. And so I've always liked this chart, even if I don't like the hurricanes, but I like the idea of how they show what the predicted path of a storm might be. So this is the cone of uncertainty. So they don't know exactly where it's going, but it's likely to be somewhere in this range. Or here's another way to look at the same concept. This is for project management. So at the beginning, you aren't quite sure how much the project is going to cost. And then as you move on, that number gets tighter and tighter and tighter until you get to the end and you get to your final price. And then the project's also completed. So during all of this, the risk is dropping. So when you get to the end of the project, or you can do anything that you can to reduce the risk, that's what we want to do. So we're going to look at an HVAC cone of uncertainty shortly. But just to remind you from back in the scaling electrification piece, these are the big risks with heat pumps. Very high winter electric bills. So A, that makes people mad, and B, if they're low income, that's going to really hurt them. So we need to be very careful to design around these things. Next one is discomfort. Heat pumps used poorly can provide very poor comfort and get lots of complaints. And the last one being really noisy HVAC, both the inside unit and the outside unit. Now, if all of these come together, or if any of them comes together, it doesn't take many bad reviews to really sink the ship of electrification, because bad experiences don't scale. So a common marketing idea is that happy customers tell 2 other people about their experience, and unhappy customers tell about a dozen. Now, if it comes to online reviews, if you're like me, if you see a whole bunch of 4 and 5 star reviews and then a couple of 1 stars, I click on the 1 stars because I want to understand, is somebody being whiny? Is it an upset ex-employee? What might it be? And if it's something that's meaty and sounds legit, it's going to slow me down quite a bit. I'm probably not going to use that person. That's what these can lead to. So this leads to poor net promoter scores. So we have to be very careful how we do this, both for yourself and as you recommend this to others, particularly in harsher climates. So next up, we need to tackle typical HVAC sizes. And all of these are done in BTUs per hour. This is the American Standard Unit. BTU is oddly enough the British thermal unit, so as with much of our metric system as opposed to metric system, it's British that we never moved to metric, so we're the only ones still on the British system. A BTU, just random trivia, is how much energy is contained in a match if you burn it from head to tail. And then taking that number further, 12,000 BTUs is known as a ton, and this is another rather archaic number. If you put 12,000 BTUs against a ton of ice, you'll melt the entire ton in 1 day. And this goes back to 120 years ago when the very earliest air conditioners were competing against blocks of ice. So once again, welcome to archaic numbers. For any European friends that are watching this, a 3-ton heat pump, 36,000 BTUs, is about 9.5 kW. Just to relate all of that back. Okay, so let's talk about the different types. So furnaces usually come in 60, 80, 100, or 120,000 BTU increments. Usually I see 60s and 80s, although I see 80s and 100s more so than 60s. And generally what we find is the 80 and 100,000 BTU furnaces are 2 to 3 times larger than they need to be, even on the coldest day, which is technically what it's supposed to be designed for, and it never is, because nobody actually does a good load calc, which we're going to get to shortly. Now, on the other hand, so the smallest conventional furnace, and this would be the smallest modulating unit that can vary down to a very low level. So it'll vary down to 20 or 30,000 BTUs, which is still, not much smaller than a heat pump over here. 60,000 is the smallest modulating piece of equipment you're going to find with any ease. There's a few exceptions, but not a lot. Meanwhile, the largest typical heat pump is 5 tons or 60,000 BTUs. So basically the 2 types of equipment touch at 60,000. Most heat pumps and air conditioners you're going to see out there are going to be 2 or 3 ton with some 4s out there, but I see a lot of 2 and 3s. So that helps give you an idea. And what we find is about 40% of homes in the Cleveland area, if they're under 2,000 square feet, if you run an accurate load calc on them, or they get some minor air sealing and insulation work, you can get them into the 2 to 3 ton range. And this is on a 5-degree day. So 24,000 to 36,000 BTUs. There's still a bunch of houses that aren't there, and they're still going to be up in furnace territory because they're so leaky or so poorly insulated. But it's surprising how many houses a heat pump will actually handle even as they stand today, which was surprising to us. Now, very important concept here, smaller HVAC is better. And this is the easiest analogy I've been able to come up with it, or to explain it. So imagine you want to take a shower and you have 10 gallons of hot water. You have the option between having a large bucket, a 10-gallon bucket dumped over your head all at once, or you can take a 5-minute shower. Which one do you want? Well, the shower, duh. Here's how this is analogous. Both of these would represent the same amount of BTUs, the same amount of heat. So we're talking the energy equivalent of 10 gallons of hot water, whatever that might be. So this is how most furnaces work. They are 2 to 3 times larger than they need to be at design temperature, which for Cleveland is 5 degrees. So we only spend 88 hours a year below 5 degrees. So it's usually a couple of nights a year. That means that when it's 40 or 50 or 60 degrees outside, that furnace is now 20 or 30 times larger than it needs to be. And that's why temperatures get really uncomfortable when it's 40 or 50 out. So if you've ever noticed your house feeling cold in those shoulder seasons, it's largely because your equipment is oversized. What you want is that nice gradual stream of water. So it's more or less the same amount of energy that's happening, although if you use a heat pump, they are kind of magical. They pull a lot of the energy they need from outside. So they use 2/3 less energy piped in than a furnace does. But what they can do, if you pick the smallest one possible and then you pick a variable speed, they have a throttle on them. So you can vary it down to a very little amount of heating or cooling, which is going to match how much heating or cooling the house needs to what the equipment is putting out. That's really, really critical. So this washes all the surfaces and materials in your house with a little bit of heat or a little bit of cool, and it keeps everything in your house within a couple degrees of what the thermostat says. That is called mean radiant temperature, MRT. Radiant heat is like the sun or a fire. It's a one-way. It feels wonderful. About 60% of human comfort is based on radiant. And you can get good mean radiant temperature. So like if you like being in a house that has hydronic heat, hot water heat, that's good mean radiant energy is what you're feeling. You can get that with right-sized variable speed pieces of equipment. The routine feedback we get from people post-project is, I can't believe this is the same house. It is so much more comfortable. One client even gave me the wonderful line. She said, it feels like you put a bunch of invisible radiators all over my house. That is what right-sized variable speed equipment can do in a house. But you need to also size it as small as you can, because if you don't, it's still not small enough to do the job and create that magic. And here's where that becomes a problem. So 3-ton heat pump is 36,000 BTUs. If I don't have any information about a house, the load calculation can easily be plus or minus 30,000 BTUs, which is basically an entire piece of equipment. So a load calculation that is off that much, it's routinely as much as plus or minus 70%. If it's off that much, it's not a calculation, it's a guess. So if you're going to take that from a guess to at least an educated guess, and preferably a highly educated guess that's still within a calculation. Because remember, we're still modeling, so things are never perfect, they're never dead on, but we can get more accurate models. So if we have energy use for a year or several years prior to look at, we can reduce that range down to plus or minus 10,000 BTUs, or about plus or minus a ton. But still, if 3-ton is appropriate, it might be a 2, it might be a 4. That's still a pretty wide range, wider than we'd be comfortable with, because you still don't know what size you need. So like this would be like going to the store, asking a salesperson what size you wear, and they tell you somewhere between a small and a XXL. You know, it's like, thanks a lot. It's no help at all. This is getting down to where we're talking small, medium, large. But where we want to get is if we have the energy use, the blower door, and some client information, namely what set points you have for your thermostat, we can get you down to plus or minus 3,000 BTUs. That basically decides on what size you need. So we'll be down to either like a small or a medium. And what this also does is it reduces the risk of those bad things happening. And when we get down into this range, if we can get down to plus or minus 3 or 5,000 BTUs, heat pumps come in 6,000 or 12,000 BTU increments. So that's close enough. We don't have to be any closer than that. But plus or minus 30,000 isn't good. Plus or minus 10 isn't good. Plus or minus 3 or 5, good enough. Because like on heat load in particular, if we're off by a little bit, we can run a little bit of resistance heat, which we'll be talking about next time. Don't fear it. Resistance is not fuel. And what this ends up doing is we drastically reduce the risks of those high bills, comfort complaints, and noisy indoor and outdoor units. And we also reduce the risk of those bad reviews and not scaling. So there we go again, different sizes. Okay, next piece of the puzzle is blower door. So I mentioned this. The blower door number, which that measures how much your house leaks. It's a relatively simple test. It's a big fan that goes in your front door. The blower door really matters to how much it takes to heat or cool your home. So these are actual load calcs from an 1,800 square foot house. It was a ranch built, I believe, in the 80s in Rochester, New York. So this house tested at a 2100 CFM 50. That's cubic feet per minute at 50 pascals. Not that it matters. This is the standard unit with a blower door in the US. That's where the house tested in now. That led to a 3-ton heat load, give or take. Like it might have been 37,000 or something like that, but give or take, it was a 3-ton heat load. Now, if we could get the air leakage down on that house, this is not changing windows, this is not changing insulation, this is leaving everything else the same. Hear me on that. This is just manipulating blower door. A 30% reduction dropped that house down to 2 tons. So once you get to some reasonable amount of R value, it's like R10 or R20, air leakage matters far more than R value, insulation value. Now, the problem with this is this house currently has a 70,000 BTU furnace, which would require triple the air leakage that it is now. So to do this, basically you'd need to leave 3 or 4 windows open a couple inches all year to make up that 4,000 CFM 50. So that's what it would take to actually make that furnace right-sized for that house. So it's way too big. And again, this is the bucket over the head. That's no good. That doesn't help anyone. And here's the easiest way we've found to look at blower door in a house. It's looking at the leakage in CFM 50 to square feet. So if you have a 2,000 square foot house with a 2,000 blower door, that's a 1-to-1 ratio. And this has been known as the LAIR, the leakage to air infiltration ratio, or leakage to area infiltration ratio. I better get that right. Thank you, Jenry Garcia, for naming it. So that's a 1-to-1 ratio, 2,000 to 2,000. That's decent. That's a B-. Fairly often we find from a 1-to-1 down with HVAC interventions alone, we can blunt or solve a whole lot of different comfort and moisture problems. Doesn't mean all of them, but at least below 1-to-1, you start having a chance. When you get above that, like say you have a 4,000 blower door on a 2,000 square foot house, which is a 2-to-1, that house is too leaky. You want to think of it like a leaky boat. So if you have a boat that's always taking on water, you don't need a bigger bilge pump. You need to fix the leaks. So this whole area here, you need to look at fixing the house and reducing how much it leaks. But you don't know where they are, and I've had houses be all over the place. I've had new houses test horribly. And actually, a good friend of mine, Dustin Cole, one of the HVAC 2.0 contractors, just last night, he had a 700 blower door target for a 1,700 square foot house, and it was spray foamed badly. It came in at 2,800, which is a 1.5-to-1 when it was supposed to have about a 0.3-to-1 ratio. So his equipment, whatever he's going to put in, is wrong now because the foam was done wrong. So this is something you don't know what's going to happen. And I tested one old house in particular, a type that's usually super leaky, and it was really tight. I didn't believe it. I pulled the blower door down. I played with all my settings. I put it back up, got the same number. So you have to test to know in this. And again, smaller HVAC is better. So you want to size as small as you possibly can to still meet your load, and then use variable speed equipment. And that reduces your risk and helps you size accurately. So here's the different things you need to have an accurate load calculation. So you need to have a blower door reading, you need to have annual energy use, both for your heating fuel, if you have gas or oil or propane, and then your electric use. You need to know the number of occupants, because if you're looking at the total annual usage, like water heat is going to vary by how many people are in there. So if you're trying to disaggregate out how much the heating is for the house, you need to know that. You need to know thermostat settings. You need to know approximate insulation levels, doesn't have to be perfect, and approximate window specs. Basically, is it single pane or double pane? is the key stuff to know. And all of this, by the way, here I am, I'm going to be plugging HVAC 2.0 the whole time, so get used to it. But it's a system we built to do all this stuff, specifically for these reasons. We're solving all kinds of problems simultaneously with this. So the Comfort Consult finds out info on what your goals are in your house, what you want to fix, what your house needs, which includes the blower door test, looks at your energy use, and then also will run a load calculation based on those numbers, so it's actually accurate. And then budget will also be discussed, because it's your goals. What matters is what are they worth to you to solve, not so much what will it cost, because those may be different things. Maybe you're going to have champagne budget or a champagne taste on a beer budget, or maybe it'll be the other way around. You don't know till you get there. But the Comfort Consult collects all of this info so that an accurate load calculation can be done on your house and the right piece of equipment can be chosen. Are there other ways to get here? Yeah. But not many people are doing it, and it's certainly not systematized. There's a backup way to do this as well. If you are a ways out from buying HVAC, I'd highly recommend getting an Ecobee thermostat, and it doesn't really matter which one because all of them do runtime tracking. Doesn't matter which model you get, they all do it. It's called HomeIQ. And they are not sponsoring this, although they would be smart if they did. But if you do this, you can see what's going on. So this is pretty cold temperatures at a client house, and this is years ago. You can see it's 2015. This is when we were first cutting our teeth on all of this. So it was down to about 0 degrees. This house had about a 60,000 BTU manual J, which is the industry standard load calculation. So at 5 degrees, and it had a 60,000 BTU furnace, it should have been running high stage, and it shouldn't have been turning off. And down here you can see heat stage 1. That correlates to this light red here, or the pink. So that house never came out of low stage in this period. There was another period a month later where it did, but just barely, and it still shut off when it was below 0. So we figured out that the actual load on this house was about 30,000 BTUs, not 60. So the load calculation was still heavy by a good margin. And this is part of what makes us much more comfortable using heat pumps than most people. But if you put one of these in and you check on a very hot and a very cold day, you'll get a reconciliation point for what your house actually needs. And that's as it stands, granted. So a couple of caveats on this: it only works with single or two-stage systems. You want to watch on a very hot and a cold day. You want to compare it to the load calculation, like I mentioned. And if you buy variable speed equipment, they all the variable speed stuff comes with a matched up communicating thermostat. Communicating means it talks to the outdoor unit, the indoor unit in the basement or the attic or whatever, but the fan part, and then to the thermostat. So those three all talk to each other. So if you want the full capabilities of that system, you have to get the upgraded thermostat. It just is what it is. And they're all proprietary. You can't pull one brand off and put it on another. So when you go to replace your HVAC, you're probably going to be gifting this Ecobee to someone. But if this helps you gain confidence in the meantime, we call this a real-world load calc, and this is a great way to double-check that the load calculation is correct. So highly recommend get an Ecobee. And this is really the only easy one. You can also do an American Standard 824, but that's a fairly intense install. Ecobee is the better path for most homeowners. And again, just to repeat, to reduce that HVAC cone of uncertainty and lower your risk to where you're pretty sure what size equipment you need blower door, annual energy use, number of occupants, thermostat settings, approximate insulation levels, and basic window specs. And again, that's all collected in the HVAC 2.0 Comfort Consult, which when we get to the Find a Contractor part, you can look for one, or you can help create a new contractor, because it's still not the biggest network, that's for sure. Okay, so that's the end of this piece. If you happen to get here because a friend sent you this video, this is part of the Electrify Everything course. If you want to get access to the rest of it, it will cost you an email and your first name. Pretty basic. The course is free. You can always donate if you like. I'll give you a few opportunities. In fact, below here you'll see a link, and if you want to buy me a beer, you can do that. a theoretical beer. But if you are interested to see the rest of this course, please sign up, and then we will move on to the next piece. So enjoy your day. I'm Nate Adams, and I'll see you next time in the Electrify Everything course. Have a great day. Bye-bye.